In this lecture, we study the AC-DC characteristics of operational amplifier. In the last lecture, we have studied the ideal characteristics of operational amplifier. Now here we will study few more, that is nothing but AC and DC characteristics of operational amplifier. Now the first one is input offset voltage. Now this is the differential amplifier. When we are not applying any input, if both the inputs are grounded, or when we are applying the common signal, same signal at both the inputs, that time output should show 0 voltage. But instead of that, it will show some value that is called the output error value. To reduce this value, how much voltage should be applied at the input is called the input offset voltage. Now here in the ideal characteristics, we have seen that offset voltage is 0. But now practically it is not possible. Practically, because of here we are using two transistors we are using. Any two transistors are not having the same specification because of the different VBE voltage. Now here and here the VBE voltage may be differ and input currents may differ. That's why we don't get a 0 output voltage. So it will give some voltage in the order of micro or milli, in the order of micro it will give. So to minimize that, how much voltage should be applied at the input, that is called the input offset voltage. Now in the pin diagram also I have said pin number 1 and 5 we are using for the offset null. By using those two pins, by connecting one potentiometer, we can minimize the output voltage to the 0. So that is the purpose of pin number 1 and 5 in the case of in the pin diagram. Okay, now this is the input offset voltage. How much input voltage we need to apply to make the output voltage to 0. And the next one is offset voltage drift with temperature. Now just now we have seen that we have studied that offset voltage. So with respect to temperature, how much the input voltage, offset voltage is varying for every degree centigrade, how much it is varying. Now here offset drift voltage is indicated by VOS and it is denoted as the difference of the two input voltages VB1 minus VB2. So how much the input voltage is changing with respect to every degree centigrade. So that is called the offset voltage drift with the temperature. And the next one is input bias current. So now here this is the operational amplifier. Here it is having two inputs and for that so input I1 current and I2 current. So for input 1 it is I1 current, input 2 it is I2 current. So taking the average of these two, and these two currents are required to make the transistor on, or for biasing purpose we are using, and average of these two transistor and average of these two currents are called the biasing current, input bias current. And the next one is input offset current. So now here we have seen that because of two different transistors are not having the same specification, two inputs currents are different. So it will, if we apply both the voltages same also, so we don't get the same currents. How much the difference, that is called the offset current, input offset current. Now here I1 current is flowing, here I2 current is flowing. The difference of these two currents is nothing but a offset current. And the next one is input impedance. So here two types of input impedances are there. One is a differential input impedance and another one is a common mode input impedance. Now if we look, if we calculate the impedance between these two inputs is called the differential input. Now in the common mode input, impedance is measured from the input to the ground. Now here this is the input one. From this input to the ground, and in second input to the ground, this is called the common mode input impedance. Now this is also, now the differential input is also measured by determining the change in bias current for a given change in differential input voltage. Now in this case it is a common mode input voltage. So this is the input impedance. Next one is output impedance. From the output terminal to the ground, if we try to measure the impedance, then how much it is, that is called the output impedance. And the next one is CMRR. Already I have explained in the ideal characteristics, CMRR means what? Common mode rejection ratio. Now it is the ratio of differential gain to the common mode gain. CMRR is equal to, here you can also write it as AD divided by ACM. D is nothing but about common differential gain, and CM is nothing but a common mode gain. When we are applying, now this is our operational amplifier. Now for the both the inputs, now for this is input 1, if we consider V1 and V2. If both two different values are, two different voltages are given at the time, what is the gain of this amplifier? And if both the inputs are same at the time, what is the gain of the amplifier? So if the both inputs are same, that time it's supposed to give the output supposed to be 0, thereby the gain also should be 0. So at the time this value is 0, so now we get the CMRR value. Ideal condition is infinite, but practically it is not happen. Why? Because when we apply the same signal also, that time instead of getting the 0 voltage, we get some error voltage at the output. With that we get the very high CMRR in practical. So this is about the common mode rejection ratio, and this we use for how much the operational amplifier is rejecting the noise or rejecting the common signals. So we don't intentionally give the common signals. So common signals are nothing but what? Noise will be added at the both the inputs. That time how much the noise is rejected by the operational amplifier, that we can calculate it by using the CMRR. Now next one is a slew rate. So slew rate is the ratio of, it is the rate of change of output voltage in response to the step input voltage. Or now here this input is applied, this step input is applied at the input terminal, and so at how much time it is reflected at the output. So that is nothing but a slew rate. Now here it is changing from 0 to high with t is equal to 0 time. Now at the output, now this is output, so it is taking this much time to change from minus Vmax to the plus Vmax. So the time is a delta t. So this is nothing but a rate of change of output voltage, nothing but what? Slew rate is equal to del V out divided by del t. Or this also we can write it as a dV0 divided by dt. So this is about the slew rate, where V out is the plus Vmax minus of minus Vmax. So peak to peak, what is the magnitude that we have to take for the V out. So this is about the slew rate. Now here we completed the ideal characteristics. In the next lecture we will see the inverting and non-inverting amplifier. Thank you.